Learning in unknowns, surveying steps toward open world recognition. Thank you.
So I'm Terry Bolt. I'm from the University of Colorado, Colorado Springs. I'll be posting a video of this afterwards, so if people want to get it, they can find out. Also, not on these slides, we have 2 faculty openings, one in cybersecurity and one in just general computer science. So what is this class? What is this subject? Do you know? A few of you might actually know it. Most of you will quickly say, I don't know. But it's important. You know you don't know. And that's what we call open set recognition. The curious among you might actually go a little bit farther, go to look it up, find some other images to learn that it's a centaur or called a cone jelly. And that's open world learning. Recognize you don't know it, go get more data, get some labels, learn it. That's what we as humans do as intelligent beings. Okay, this problem is pervasive across lots of issues. So yesterday there was a nice talk, traffic cam, from Abby and Robert Plus looking at hotel rooms, and can you recognize them? The problem is in the real world, the perps will often upload images that have been modified by some filter, and it breaks their systems terribly because they never learned the modified posterized versions of the images. When we have to deal with adversaries, they will do things to break your system. Nature is its own adversarial example. Can you count how many cars are in this scene? This is from an example one of my student companies is doing. There's ice on the camera. You really can't tell, but you instantly know you don't know how many cars there are, right? And nature will put out bugs, birds, all kinds of stuff. Okay, here's a face recognition problem. The problem is these 2 things on the right-hand side were accidentally detected by the face detector. They go into the model, and now the best match is this person in a football helmet. Not a good score. How about these images? This is images that aren't even a face. Not only does the system find a match, it finds a match that it is supremely confident matches. What went wrong? Okay, when we're doing learning, absence of evidence is not evidence of absence. But if I look at how classifiers work, being far from the boundary will give him very high probabilities in softmax or SVMs. We can't solve this problem with Bayesian reasoning because we can't reason about the unknown unknowns. There's no way of knowing their probabilities. So the open world, the open problem is something where all of those unknowns may show up that will be absent during training. How do we build intelligent systems that understand that they don't know? So if we look at how these problems are arranged, we have the closed set training, which dominates still all of our problems. We have very open set recognition, which is clearly, we have a bunch of objects and then a bunch of unknowns. In the middle are a bunch of problems that lots of people think aren't even in this category. Face recognition detection. People think it's a binary question and must only be 2 answers. Match or no match, detect or no match. The real answer is, we surveyed in our paper 90 different papers from 14 different application areas. Even in those binary problems, the answers really should be match, no match, or I don't know. Because if it's not a face, I shouldn't say it matches or doesn't match. Okay. Lots of people think, can't I just use probability thresholding? Unfortunately not. So in the 70s, Chow had a nice paper. They looked at the regions. You find out where they're uncertain. You can make your recognizer better, but it doesn't really scale. If I do that in a multi-class problem, and now I sort of zoom out and say, what happens in the bigger picture? Right? Those lines, those separation regions go on forever. They label Mars. If I start putting things out in that space, I'm going to label everything. In fact, I'm going to label them extremely confidently because they're far from all of my boundaries, and so I get really bad results. So we've been working on this problem for a long time, in part because of my own companies. I was having real problems with real data. We formalized this as breaking this up into 2 parts, what we call open space risk and empirical risk error. That's the normal area you look at. But we want to put in a penalty that says you've got to pay a price for labeling things you should not label. Okay, and we have some regularization constant between the 2 of those that we want to play with. So we can do that in a very simple way by saying, let's take the volume of space that you label, that's the thing on the top, that you label positively, you label it as belonging to some class, and just normalize that by how much should be labeled. And that's our ratio, the open set risk, that says how much space have I labeled that I shouldn't have. If that number is infinite, because I've labeled all of space with some class, I have a real problem. There's no way to regularize it. Anything else I can sort of play games, So is there a question? Are there other algorithms that solve this? There's actually a whole bunch of things like RBF SVMs, KDEs, GMMs, SVDD, well-known algorithms that sometimes solve it, okay? But none of them always solve it. We've invented a class of algorithms like WSVM, NNO, EVM, which I'll talk about in a second, that probably solve it all the time, okay? And you have to, the biggest thing you have to know is anything that labels all of space, an infinite amount, like a linear classifier, an SVM, they'll have unbounded open space risk and they just never solve the problem completely. Can I solve this with novelty detections, anomaly detection algorithms? Yeah, sort of. Anomaly detectors don't actually do multi-class. They say anomaly or not. right? You really want to put all of your errors together and say, not just anomaly, it's anomaly or what are the individual classes. So one way of looking at open set recognition is it's anomaly detection plus multi-class recognition done simultaneously. So you balance the errors, not view it as two-stage problem. You can do it as two-stage problem, but in all the experiments we found, the errors are much higher if you do it that way. So let's look at some other thresholding. So if I look at the numbers, 1, 2, and the question marks here, the bottom shows you a binary SVM, the top is a one-class SVM. One-class SVM shows the pink region. It does a good job of rejecting the unknowns, but it also mixes the classes together. The binary SVM, even though it's binary, labels all of the space blue on the right-hand side. The new kinds of algorithms we work out have things that always have bounded regions. They're always compact in space, and that allows them to limit how much they label when they shouldn't. And we actually call that the compact debating probabilities, and although I conjecture I haven't been able to prove that all things that are provably open set have this property, it's a pretty good basic idea. If you can bound your function by something that is going down to 0 in one lump, then you can always threshold and find some place where it will work. You can even take existing functions and make them behave that way. So our WSVM is really a one-class SVM multiplied by some EBT scaled version of a binary SVM. So the one class makes it behave. There's lots of problem variants in this space. So there's 3 other talks here at AAAI. There's a zero-shot learning paper, and then 2 other papers tomorrow you can look at. Okay. I said towards open world learning. We define open world in a very special way. We start with open set recognition. You got to recognize I don't know. Then you have to somehow magically get labels, which may be learning or not. Then you have to do incremental class learning and go back and update your representation. So I'm recognize I don't know, I'm going to learn about it and then bring it back in. And if you really want to be gutsy, you try and do that where you actually change your feature set in an open world, deep network sense where you're doing feature learning at the same time. That's really hard. But that's what open world learning is. I don't know, I recognize I don't know, I get some help, I label it, and I iterate that process. Okay? There's a whole bunch of things in this space that are related in terms of few-shot learning and incremental learning. They're all pieces of this much larger problem. We developed an algorithm that was published last year in PAMI called the extreme value machine, which uses a new kind of nonlinear thing based on our margin distribution theorem. These basically build these little Weibull balls around things, and then when I need to, I can add new data. The Weibuls see their new extreme values. They contract to allow us to do this in a nonlinear kernel function that's way more efficient than a nonlinear SVM, but still has lots of nice properties. So that works in both classic and deep learning and has allowed us to do very good at what we need to do for some classes of problems. A couple years ago, though, we had this change to things called deep networks. We've been working on this in classical networks. We started looking at how do we do this for deep networks. So the basic idea is we take something in a feature space, some high-dimensional feature vector, we build its representation. In this case, it's a simple mean vector. We can then take that, we can use extreme value theory to talk about how to normalize it, build a representation, and that gives us a cap model that we can then threshold. By doing that, we can actually solve a bunch of problems that people were having. So we can take a real image, we define an open max, does normal behavior. We take one of these Foley images from Jeff Kuhn's group and all. We recognize it as unknown, and we take some of these unknown objects, and we can classify them as unknown, even though our network was only trained with a bunch of knowns. So we can convert the knowledge of what everything we saw was during training to sort of say, look, that's not like my training, it's unknown. But we tested on real problems. It didn't work as well as we wanted. We have to understand why. So I'm going to illustrate this with some examples from Linnet++ in 2D. So we have our knowns and these digits. We have some letters. And then we have some unknown Devangari Indian script. And so if I take my network and I build my EVM model, I sort of draw a series around them. Okay, I can sort of say, okay, this is the red class, this is the purple class. But now when I take unknown objects, these letters, and I push them through the network, they're the black dots. They're everywhere. But they're not off in space like they were with other feature spaces. They're on top of everything else. There's no easy way to separate them. So we started digging into that and looking at what's going on. We recognized 2 interesting things. The unknown samples actually had smaller magnitudes and higher entropies, on average. But they were pretty much everywhere. So we want to find some way to emphasize that. So we started designing a technique that we presented this year at NeurIPS that tries to make the unknowns go to the middle and all the knowns go out farther in space. So if we do that, we can take this diagram where we have, the red lines here are showing you the magnitude, the frequency of the unknowns. We can compare this to a background classifier, which says, I have these known unknowns I'm going to train on. This is a classic thing we do in vision. Here's a bunch of known unknowns, call them the background. And then we can use our thing we call objective sphere. And you'll notice that the errors, the red line in the drawing, right, is doing much better on our objective sphere. We have much lower high confidence unknowns. There's still some of them because unknown unknowns are really hard to train against. But we got some robustness in our system by building a system that takes its background classifier and shoves it in the middle and modifying the magnitude of the features. And that gave us some really good insights into how to handle the problem. If we look at the actual performance on a large-scale data set, we have two different error messages we looked at. The red and the green are new algorithms. Orange is the background classifier, which was sort of the next best source. That open max thing I talked about is way down here. It doesn't work at all in this 2D version. It actually works better in higher dimensions. Now, not all is lost as we start looking at these things, so I want to talk about some positive things. There was a really nice paper at AI Stats a number of years ago where deep learners actually benefited more from out-of-distribution data. So if I actually build my network, making it solve problems it doesn't have to solve, these out-of-distribution problems, I can actually make my network better. So there's some interesting insights in that I think will be helpful as we try and move forward. But on the negative side, and this is not in the paper, but because I didn't want to be too aggressive, but this is senior member talk, I want to talk about some issues. Who are these two people? Well, according to VGG2, which is a really good algorithm, using cosine distance set at a threshold of 10 minus 4, those are both Barack Obama. Okay? These are adversarial examples. If you haven't seen these things, images that are arbitrarily close can be arbitrarily close in feature space and far away in image space. These completely break all of this stuff we talked about, because if near is not near, it doesn't work. So we can't reason our way out of this with a Bayesian point of view. We can't possibly sample it. We really have to develop algorithms, and I believe higher level reasoning algorithms, which is why I'm talking about this at AAAI, right, that help us understand when we don't know, right, it's not going to come from just statistics. It's not a mapping function. So let's embrace the unknown. Join us in taming it. Questions?
Great talk. We have time for a few questions. Go ahead, Ben.
Unlike BaseNet's probabilistic logic programs let one represent the nation is better, also undefined true values is a form of don't care. Those are basic tools for working with probability and probabilistic logic. They supersede the expressiveness of BaseNet. Have you looked at using those to represent unknowns?
So, not in 15 years. So, no. Not recently. I mean, there's still the problem of, as soon as you add negation, your space often explodes exponentially large, right? And when you're dealing with the class of all objects, right, trying to bound it will be difficult, but I will have to look more deeply at that.
Well, there are efficient inference techniques that work with that technique.
You say there weren't 15, 20 years ago, but there might be now, so I have to go back and look at it. Other questions? Comments? Someone will tell me I'm wrong? I'm happy. Very quickly, because he's about to take the screen, but... So text me afterwards, I'll hang it out. So the name of my lab is BAST Lab, so the URL was github.com/BASTLAB. That's where I post the video.
Yes, please. All right, so thanks very much, Greg. Greatly appreciate it. So I hope it was clear he was making requests for people to come up to him and talk to him about how people contact some of the things they're used to in the direct economy. Some of you work